Right Academy. Learn it, teach it, remember it. Today we're building the Failure Modes Toolkit. Everything in a distributed system fails eventually, so we'll learn the moves that turn a failure into a blip instead of an outage. You detect it fast, and then you recover with a move you prepared in advance. Here's a system you've seen 100 times. A client calls a gateway, the gateway calls a service, and the service reads from a database. The requests flow along these paths. When everything is healthy, a request goes straight through and comes back served. Now, a fact of life. That database will fail. Disks die, processes freeze, networks drop packets. Suppose it goes dark for 3 seconds. The requests in flight slam into a dead component, and they come back as errors. So here's the question. In one design, those 3 seconds heal themselves. In another, the same 3 seconds snowball into a 40-minute outage. What separates the two? Failure is certain. The outage is optional. Think about how a building handles fire. Nobody fireproofs a building by hoping. Kitchens catch fire, wiring shorts. Instead, every room gets 2 things. A smoke detector on the ceiling, whose whole job is to notice within seconds. And a sprinkler beside it, a prepared automatic response that contains the fire to that one room. Watch it work. A fire starts. The detector trips almost immediately. The sprinkler douses it. And the building survives with one scorched room. That is the entire mental model for this lesson. Every component in your system is a room. For each one, we'll name its detector, the number you watch, and its sprinkler, the prepared move that recovers. A detector and a sprinkler per room. Let's start with the most innocent-looking tool in the box, the retry. A service calls the database, the call times out, so it simply tries again immediately. What could be kinder? Well, zoom out because it was never one caller. Say 100 requests a second flow into this database, and it stumbles for 2 seconds. Every request that failed retries instantly on top of all the new traffic still arriving. Watch the load. It was struggling at 100. Now it faces 300 at the exact moment it is weakest. Work arrives faster than it can be served, so a backlog piles up at the door. And when the database finally claws its way back up, that whole accumulated herd charges through at once and knocks it straight back down. This is the thundering herd. The friendliest tool in the box just became the attack. Here's the insight that fixes it. When something is failing, don't lean in. Back away and back away fast. Wait before you retry and double the wait each time. The first attempt fails, so wait 1 second. It fails again. Wait 2. Then 4. Then 8. Every failure is more evidence that the thing is really down, so you give it exponentially more room to breathe. Quick check for you. The 4th attempt just failed. How long do we wait now? 16 seconds. The doubling continues. 2 details make this production grade. First, cap the wait, say at 30 seconds, so a long outage doesn't push retries out to absurd hours. And second, set a budget. After enough attempts, you stop, declare the call failed, and hand the decision up a level. Infinite patience is not a strategy, but exponential backoff alone has a sneaky flaw. Picture 3 clients, or 3,000, that all saw the same blip at the same instant. They all fail together. They all wait exactly 1 second. So they all come back at the same instant, a synchronized wave. Then another wave at 2 seconds, and another at 4. You didn't remove the stampede, you scheduled it. The fix is almost embarrassingly simple. Add randomness. Each client waits a random amount between 0 and its backoff, which is called full jitter. Now watch the same 3 clients again. Their retries smear out across time. It's the same total work, but spread into a gentle drizzle instead of arriving as spikes. The recovering database sees an absorbable trickle, comes back, and stays back. The whole recipe in one breath. Retry, back off exponentially, cap it, jitter fully, and stop at a budget. Back off protects a dependency from repeated pressure. But if that dependency is going to be down for minutes, even patient retries are waste. Every attempt burns a thread and a timeout, and your own service backs up waiting on a corpse. For that, the next tool, the circuit breaker, named after the switch in a fuse box that cuts power before the wiring melts. It sits on the calling path, and it lives in 3 states. Closed is normal life. Requests flow through, and the breaker quietly counts recent failures. Watch the requests flow. Now the dependency gets sick. Failures climb, and the moment the rate crosses a threshold, the breaker trips open. From now on, calls fail fast. They're rejected right at the breaker without ever touching the sick dependency. Your service stops wasting threads and serves a fallback instead. And the dependency gets the one thing it actually needs: silence. After a cooldown, the breaker goes half open and lets exactly 1 probe request through as an experiment. Suppose that probe fails. Where does the breaker go? Straight back to open for another cooldown. But when a probe finally succeeds, the breaker closes and normal traffic resumes. 1 probe, not the whole herd. The same herd taming idea in miniature. Retries and breakers handle a component that's temporarily sick. But sometimes the machine is simply gone. For stateful components, the database leader above all, the recovery move is failover. You keep a warm replica that continuously receives the leader's writes. Watch a write reach the leader, and the leader streams it down to the replica. And you watch the leader with a heartbeat. Every second it says, still alive. Then the leader dies. Count the silence. 1 missed beat could be a network hiccup. 3 in a row and we declare it dead. So promote the replica to be the new leader and reroute the writes to it. Now the writes land on the new leader. But notice the price. 3 seconds to detect plus about 2 seconds to promote is 5 seconds where writes stall. You can tighten the heartbeat to shrink that window, but you raise the odds of a false alarm declaring a live leader dead over 1 dropped packet. Every detector in this toolkit carries that same trade. And now the gotcha that interviewers love because it separates careful thinkers from memorized answers. Here are the 2 leaders and the storage log they share. The old leader was never actually dead. It was frozen. Maybe a long garbage collection pause. Maybe a network partition. We declared it dead and promoted the replica so the epoch counter ticks up. And then the old leader wakes up, and as far as it knows, it is still the leader. 2 leaders, both willing to accept writes. That's split brain. Here's the fix. A fencing token. The new leader writes with token 8. Storage only honors the highest number it has ever seen, so it is accepted. Now the zombie wakes. It writes with token 7. Rejected. And the zombie learns of its own death from that rejection and steps down. 1 incrementing integer closes the split brain hole. A paused process is not a dead process. So far we've assumed failures announce themselves. They don't. You have to instrument for them. Here's our little system. A service, a database, a queue, and a worker draining it. A detector is nothing mystical. It is a number you watch, a threshold you trust, and a page. 4 meters cover most of the failure surface. First, the heartbeat gap. Second, since a component last said, alive. That's your dead machine detector, and it's the one that drives failover. Second, the error rate. The fraction of calls failing over the last window. That's your sick dependency detector, the one that trips the breaker. Third, tail latency. How slow the slowest 1% of requests are. That's your early warning, because systems get slow before they get dead and the tail moves first, long before the average twitches. And fourth, queue lag. How far behind a consumer is running. A backlog that grows faster than it drains means something downstream has stalled. And if the lag ever threatens to outlive the data's retention, you page immediately because past that point the data is gone before anyone reads it. Now let's assemble the toolkit the way you'd close a design review. Here's the full system. A gateway, a service, the database leader with its replica, a third-party dependency, and a queue draining into a consumer. The service is really a fleet of instances. We walk it box by box, and every box gets its detector and its prepared recovery. Start with a stateless service instance, and let's kill one. Its heartbeat goes silent. That's the detection. The recovery. Pull it from rotation, and the requests in flight retry against a healthy peer with backoff and jitter. Nothing is lost because it held no state. Into the table it goes, row 1. Next, the database leader dies. You know this one now. 3 missed heartbeats, promote the replica, fence the zombie with the new epoch. Row 2. Next, the dependency starts timing out. The error rate crosses its threshold, the breaker trips open, and callers fail fast with a fallback while one probe hunts for the recovery. Row 3. 2 rows to go, and they're the quiet ones. The queue's consumer stalls. No crash, no error. The backlog just grows faster than it drains. Lag is the detection, alarmed well before it threatens the retention window. The recovery. Scale the consumers out and the backlog drains. Row 4. And finally, the poison message. One malformed message crashes the consumer every single time it's retried, and the whole queue backs up behind it. The detection is that one message's retry count climbing. The recovery. After the retry budget, move it to a dead letter queue, let the healthy traffic flow past, and let an engineer examine it offline. Row 5. Now read the finish table. The failures differ, the tools differ, but every row is the same sentence. Watch a number, and when it crosses a line, run the prepared move. That table is how you close a design, and it's how you close an interview. 4 details decide whether this toolkit works when it matters. First, retries need idempotency. A timeout doesn't mean the operation failed. It may have succeeded and lost only the reply. Retry a payment blindly, and you can charge the card twice. So give the server an idempotency key to deduplicate on before you make retrying automatic. Second, layered retries multiply. If the edge tries 3 times, and the service tries 3 times, and the storage client tries 3 times, one click becomes 27 calls at the bottom. Retry at one layer and give the request one shared budget. Third, a breaker needs its half-open probe. Trip open without one and it stays open until a human notices, so recovery needs a deploy. The probe is the automatic path back. And fourth, failover without fencing is not failover. It's a data race with the scheduler. A garbage collection pause is all it takes to mint a zombie. So here's the whole lesson in one picture. And the standby is not the backup. That distinction matters. That distinction matters. That distinction matters. That distinction matters. The outage is optional. You can't stop components from dying, so you stop trying, and instead you give every component a detector and a sprinkler. Watch the system heal itself one more time. The leader dies, the heartbeat notices, failover and fencing take it. A dependency sickens, the error rate notices, the breaker takes it. The backlog grows, lag notices, and scaling takes it. And when someone points at any box on your diagram and asks, "What happens when this dies?" your answer is 2 short sentences. How you detect it and the move that recovers it. Detect, then recover. Want to keep learning? Come find us at academy.rudewrite.com.